Hello and welcome once again for another ES340 video. This is day 7 part B and this is the energy balance for ideal gases. So a thing I wanted to note, which is why I wrote it right up here so I wouldn't forget to note it, is that we generally choose the reference value so that in this case, the specific enthalpy is equal to 0 at a temperature of 0 Kelvin. Okay, so basically the unit, we could have chosen this in some kind of arbitrary manner, and this makes a lot of sense to choose it in this way. But what that means is when you're dealing with, and this is true for other quantities as well, these reference points, what that means is that when you're doing calculations, you should use absolute temperatures, which would be either Kelvin or Rankine, depending on SI or English units, rather than the non-absolute ones, which are things like the Celsius scale in SI or the Fahrenheit scale in English units. Okay, so you do, when you're doing this, unless it's a difference of temperatures, in which case it doesn't matter. Or a rate, only if it's a difference. Unless it's a difference in temperatures, you have to use the absolute temperatures scales, okay? So keep that in mind. If you want to be safe, you can convert everything always to absolute temperature, and that obviously would be perfectly fine. But in any case, for ideal gases, what we find is, again, that we have the equations for our change in U, which I'll write as U of T2 minus U of T1. Oftentimes we'll just put a U2 minus U1, same idea, is equal to CV of T2 minus T1 if CV is constant. Now, why is this the case? Again, ideal gas, of course. Well, we can see quite easily that using our integral, right? We know that delta U was equal to the integral from T1 to T2 of CV of T dt. If CV is a constant, just equals to a constant, say CV, why not? We'll call it that. Then delta U would be equal to CV times the integral. I'm pulling the CV out, right, because it's a constant, T1 to T2 dt. And obviously that integral leads to this, right? It's the same idea for the if Cp is constant, same exact idea. Delta H is equal to Cp times T2 minus T1, or Cp delta T, right? So Cv delta T for delta U, Cp delta T, again, these are for ideal gas, for Cp delta T for delta H, okay, where this is obviously the enthalpy and this is the internal energy up here, the U, right? So that will lead us into a clicker question now. Suppose instead of CV being a constant like we had above, that CV times T was equal to a constant. What function of T would be appropriate for finding the internal energy, and I'll make this should have been something like C, some constant. Let's call it a capital C. No, that's right. I had this right because this is CV was the constant. Sorry, CV is a constant here. Okay, so would delta U be equal to, in that case, in that kind of scenario, would delta U be equal to CV divided by T2 squared minus T1 squared, and so on. Okay? Now for polytropic processes with ideal gas. So recall, for a polytropic process, that PV to the n is equal to a constant. That means that that implies that P1 V1 to the n is equal to P2 V2 to the n, right? And we can rewrite this as needed. So basically, if I divide the P1 over, and then divide the V2 to the n over, and then obviously I can pull the n out based on the exponential rules. I can pull that n out, and this is what we get. Okay, so this is quite convenient. But in the case of an ideal gas, you can recall the following, that PV is equal to, well, it's really PV is equal to RT. That was an ideal gas, right? Which means that PV is equal to MRT. So that I can actually take this and do some rearranging here. So that means that P1 V1 is equal to MRT1, P2 V2 is equal to MRT2, right? So I can then find this ratio that I want up here, which is P2 over P1 must be equal to M RT2 divided by sorry, and I forgot my V2. It has equal to this MRT1 V1 over V2. Okay, so that comes directly from the relationship here, and we can continue onwards. Obviously, the M's and the R's cancel out, and what we're left with, I'm going to run out of room, so I'll skip past the clicker question, and I'll come back to it in a moment. This means that P2 over P1 is equal to T2 over T1 times V1 over V2. Now, skipping past the clicker question, remember for a polytropic process that this is true. So I can replace P2 over P1 with V1 over V2. So what that means is that T2 divided by T1 times V1 divided by V2 is equal to V1 divided by V2 to the n. Again, because of this relationship up here, I'm just replacing that down here with that, which means that T2 over T1 is equal to V1 divided by V2 to the n minus 1. So we actually can get a relationship like this. I'm not going to work through the other one, but you can work through it yourself. So what we find is that T2 over T1 is equal to P2 over P1 all to the power n minus 1 over n. And that's also equal to V1 over V2 to the n minus 1. Okay, so we have this nice relationship. Again, all of this is for an ideal gas. And we can furthermore work this out, and we can figure out what the work would be in the case of an ideal gas. Well, that's equal to the integral of T1 to T2 of P times dV. And it turns out that we can get a nice relationship for this by using these facts here. We can find that we get mR times T2 minus T1 to the n minus 1 if n is not equal to 1, or we can find for n equal to 1, this is equal to mRT times the natural log of V2 over V1. Okay, now as you already know at this point, I find it much easier to, rather than trying to write down all these formulas and all this stuff, to actually perform the integral to find the work. But if you want, you can do this in the ideal gas case and have these equations. You can have these equations written down. Now I skipped over the clicker question, and that's where I'll end for today. Right down here. For which value of n may we take the pressure of a polytropic process to be constant? Remember, PV to the n is equal to a constant. Is there any value of n that we could take P to be constant? That's all that I have for this video. Hope to see you again soon.